Okay, today we're happy to have John Dewar give a talk. He is at the University of Bristol at the moment. He has his degree from University of Lancaster and has worked in several groups in other places, such as the Fields Institute and at the Radon Institute. And he's going to tell us about stuff accounting realizations for rigid graphs, and I will let him speak.
All right, thank you very much. So let's get started. So my talk's going to basically be split into three parts. So the first is going to discuss realization numbers of graphs, what that means, how we define it, and so on and so forth. The second part is going to discuss how we can do non-Euclidean versions of this, and non-Euclidean meaning kind of spherical hyperbolic spaces. And then the last part of the talk is going to compare the two. And I'm just going to give a survey of various results, and I'm going to mention some of my own results in recent years and some very recent results as of last week. It's a very small result, but it's quite a nice one. So, right. So, starting off, when I'm talking about stuff, I'm going to talk about graphs. I'm only ever going to talk about finite simple graphs, so finite vertices, no loops, no parallel edges. In the setting I'm in, it doesn't make any sense to do anything else. A d-dimensional real realization of a graph, and I'm stressing the word real because that is not going to stay the whole way through the talk, is just going to be a map from the vertices to RD. So it's just the vertices. It's not a graph embedding in a topological sense. I'm not embedding edges as lines. I'm just embedding the vertices. The edges will just be kind of considered distance constraints or like stiff bars, but we do allow them to cross. So it's not topological in that sense. Real framework is going to just be a pair, so a graph and a realization. And I'm going to often talk about equivalent frameworks. That's just going to mean that they have the same edge lengths. So in this picture below, you can see two-dimensional frameworks. And these two are equivalent. So all I've got is a triangle with a rectangle with a brace, and then I flipped over one of the triangles with a reflection. But the edge lengths between the two of these are equal. Okay. I'm going to say then this is very rough, and I'm going to give a much better definition later because this is kind of the wrong definition. Is that the number of equivalent the derealization number of a graph is going to be the number of equivalent real frameworks modulo isometries. So you just mod them out of a kind of a randomly chosen d-dimensional framework. But like I said, don't be too committed to that definition because it's wrong. And the reason for that is this definition doesn't really work. So it's not consistent, right? So on the top, I've got what I'm going to pretend is a randomly chosen or a generic a real framework. So it's basically the one that I had previously. And I've attached a very long set of edges connected to a vertex that flips over like so. Okay. And you can kind of unfold this thing, and this thing will go like this. Okay. So you just unfold it and you do that. But with the other one, I've picked another, what we're going to pretend is random realization. And this can't happen because the two edges are too short. So we can't open up the triangles as we did before. So the realization numbers between these two different realizations are different because we're using real geometry, and that's a problem. So the solution is to use complex realizations. So we allow for complex realizations, and this will act as an upper bound regardless anyway. So I'm now going to say that a d-dimensional complex, but if I forget the word complex, I mean complex, realization of a graph is going to be any map that takes the vertices and puts them in CD. Okay. Distance is now going to be a quadratic form, not a norm. So to be clear, this is not the complex norm squared. This is a quadratic form. It's kind of a slight abuse of notation. So it just takes a point and sends it to its coordinates squared. And obviously, if you do stuff like this lovely triangle down here is an example of how things can get a little bit weird. We have a right angle triangle, and if you do the Pythagoras equations, you end up with one edge squared plus the other edge squared means that the diagonal has to have length 0. So you can kind of say weird stuff with quadratic forms. This is because they allow isotropic pairs of points in some sense. So just to be warned, quadratic forms can be a bit weird. They're mostly well behaved. So going about that in a second. Isometries now, when I say an isometry, I'm going to mean an affine map. So it takes a point, it's going to multiply it by a orthogonal matrix. So just a matrix that satisfies these equations like so. At the top. Examples of this are just going to be the stuff I've got below. So a normal rotation matrix for any theta, that will be still an orthogonal matrix. But you can also get these kind of bizarre things that I've got lined up here with this kind of 2s and the I root 3s and stuff. This is still actually a linear isometry in this sense. And you can actually kind of prove that you can prove all isometries of a complex quadratic form is going to be of this form. It's going to be affine. One part is the orthogonal matrix and a translation. Okay. Got to be a little bit careful because isometries can behave quite weirdly. What we like in rigidity theory when we're dealing with real spaces is the fact that if I just want to talk about two things having an isometry that maps them between them, it does. If I want to say that something can only be mapped to isometric copies of itself, it's enough to just check that all the distances stay the same in some sense. But this doesn't work in these cases. And here's an example of 2 points where they have the same distances between them, i.e. 0, but there's no isometry that maps from one to the other. Okay, so things can be a little bit bizarre. Fortunately, this doesn't occur most of the time, and it doesn't occur if you have enough points. So if you have a point set that is affinely spanning, this sort of weirdness can't happen. I just thought I mentioned it to be kind of honest about how these things can be a little bit bizarrely behaved. Okay. Right. So with that, I'm going to do rigidity in complex spaces. So I define this lovely function, the rigidity map. So it just takes a realisation, a complex realisation, which you can always think of as being in the space CD to the V, and it maps it to its set of edge lengths. And you do this by taking the point and mapping it to its edge lengths. I'm dividing it by 2 just for differential reasons later on. It's to do with the rigidity map. It's not that important. So you can imagine the half's not there if you prefer. Okay. We're then going to say that any two d-dimensional realisations of a graph, we're just going to say they're equivalent if they have the same set of edge lengths. With our language, with this rigidity map, we can now say they're equivalent if they map to the same point under the rigidity map. We're going to say that they're congruent if an isometry maps from one to the other. And I'm going to denote this by tilde. This is an equivalence relation, and I will be using it later. So I can just have an equivalence relation of realisations by doing so. With this, I define a d-dimensional framework to be rigid if I have, this condition is slightly wrong, but it'll be fine. The rigid definition is slightly iffy, but effectively, what's a better way of putting it? If there was some sort of continuous motion of the vertices that preserved the edge lengths and didn't come from a family of isometries, then I would say that the framework is not rigid, and rigid is the opposite of that. Alternatively, you can think of it as like a local property, and that's why this definition is a bit hokey, so I'll need to correct that later. Global rigidity is where if I take if I have my framework and I take an equivalent d-dimensional realisation, it's congruent, and it doesn't matter which one I pick. And this is what global rigidity says. So rigidity, it's got this kind of hokey definition here. You can think of this as kind of locally rigid. It's the only one where locally anything equivalent has to be congruent, and global rigidity is anything that's equivalent has to be congruent no matter how far away it is. Okay, so apologies about the definition being a bit hokey. You can still just picture it as being the kind of, this is flexible, and if you put a brace in, it's rigid. That still all works. Okay, so I've defined all this. We kind of want to talk about things generically, because that's kind of what I'm interested in, is combinatorial rigidity. So generic here is just going to mean that the coordinates of my realization are algebraically independent over the rationals. And with this, I would say that a graph is, in brackets, globally rigid or just d-rigid, if it has a generic globally rigid or just rigid d-dimensional realization. Okay? So the picture below, I've got a picture of a graph that's on the left is rigid, and on the right is not rigid. And if I wanted to get a globally rigid one, I could add an additional brace across to the graph on the left. Okay. Now, I've gone through a lot of definitions, so apologies about that. But the point about this is that I have done all this complex stuff. I've got this kind of definition of graph rigidity, and it is actually exactly the same as what it would be in the real case. You can kind of just keep, if you want to do the combinatorial stuff, you can just kind of keep in your head the idea of real rigid frameworks and stuff like this, and real rigid graphs, and it's identical to the complex case because I'm doing everything generically. There's no basic issues there. This all works because effectively rigidity and global rigidity are generic properties. It's quite easy to show this in the complex case. When you're doing the real cases, it's easy to show that generic rigidity in this kind of sense is a generic property. Global rigidity is quite hard. You need to use quite a lot of theorems involving stress matrices and so on and so forth. But I won't be covering that in the talk, but just as a heads up. It's kind of easy to see why the complex definitions are nicer, just because of some algebraic geometry that comes through. Right. Okay. So, counting realizations. Algebraic geometry observation, the cardinality of this configuration space. So this is the set of points. If I take my framework GP, I take all the other d-dimensional realizations that are equivalent, and I quotient out by isometries. That's what this set is. The cardinality of that set is going to actually be constant over all generic realizations. This is just kind of a nice product of algebraic geometry. The fact that this rigidity map is defined by rational polynomials. Okay. So with this in mind, I can define these, what a realization number of a graph is. So I'm going to say that the derealization number of a graph is the cardinality of this configuration space for any generic d-dimensional realization. And I'm going to say that the real d-dimensional, the real derealization number of a graph is going to be the maximum cardinality of this set if I just restrict myself to only real realizations. So I take my configuration space and I just restrict to the real realizations. I think the notation is a bit funny here. The bracket should be to the left of the RDV, so apologies about that. Quick warning, some papers, including Borsier and Strainu's paper on the topic, they only quotient out by the special orthogonal matrices. So that'd be rotations, translations, but not reflections, effectively. All this does is just double the number. Okay, so it's not actually an issue when it comes to it. You just need to keep it in mind if you're ever reading any of the literature that sometimes the number will be double and sometimes it'll be half. So there seems to be no actual consensus on the topic about what you should do. I go for the smaller number and quotient out by more, but some people don't do that. That's a matter of preference. Okay. So first observations about these things. The real number is always less than the standard derealization number. That's just true for any graph. You're just allowing for more realizations, so that's going to be true. The two numbers are finite if and only if the graph is d-rigid. So you're only going to have finite realizations if and only if the graph is d-rigid. You're only going to have one realization in the complex setting if and only if you only have one realization in the real setting if and only if your graph is globally d-rigid. And that's kind of a non-trivial result in that, yet again, involves a lot of stuff about stress matrices and stuff like this. Some of these implications you can prove quite easily, but some of the others are not so easy to do. There's some obvious ones. So if I have a graph and I take a if I take a graph H and I have a spanning subgraph of it, then the realization number, so the spanning subgraph has to have more realizations than the graph. And this is just because when you're effectively throwing in extra edges, you're adding extra distance constraints, which means you're limiting the number of realizations. If you have a framework that's not generic, but it's regular in a kind of a sense, like a differential geometry sense, then you can actually still bound its number of realizations by the complex realization number. But that's not necessarily true with the real realization number. You have to be a little bit careful. So this realization number is quite useful. You can use it to bound the realizations of any framework. Or most frameworks, as long as they're kind of well behaved. And then the last point is just that it's very easy to characterize what this thing is for the one-dimensional rigidity. One-dimensional rigidity is actually just being connected. So being a connected graph is quite easy to show. And in this setting, it's effectively kind of, you look at your two connected components of your graph, and then you're effectively just gluing them at vertices. And you just count how many times you do that, and you do it 2 to the power of it. Because if you had one two-connected graph, another two-connected graph, glue them at a vertex, then you have this, and you also have this. So you have two realizations in this sense. Okay. So these are just some kind of easy observations to make using previously known things about rigidity theory. Okay. So if I take the 3 prism, so just this graph here, then we can actually check that its complex realization number is 12. And an example with 12 realizations has been found, and this was done by Cyprian Borsier and Iliana Stranu 20 years ago, I guess now. So here's a example of a real realization, and then all its equivalent other realizations. And the colors match up throughout the graph, so you can see that it's all consistent. And this is courtesy of my co-author, Georg Grasegger, who's very good at LaTeX and ticks and drawing pictures and stuff like that. Okay. All right. So how do we go about computing these numbers? So it's easy to see that in one dimension, so one-dimensional realization numbers is very easy. For high dimensions, it gets very, very hard, very, very fast. So firstly, computing RDG is basically impossible most of the time. It's just too hard because you never quite know if you've got the realization with the maximum number of realizations. You could check a lot of frameworks and you can never guarantee it. So it's not worth looking into. You can prove it for certain types of graphs, like caudal graphs and stuff like this, but you're doing it for very specific families of graphs. We got a little bit more leeway with the derealization number, the complex version. And this is kind of true in algebraic geometry in general. Real solutions are difficult. Complex solutions are easier, not necessarily easy, but usually easier. So here it's computationally horrible, but it is doable. And one method that is a kind of a speed up is you generate a random realization, you compute its edge lengths, and then you just solve multiple quadratic equations using Grosvenor basis to figure out how many solutions it has. This is unfortunately very slow, and it is actually probabilistic because I generated what I claim is a generic realization, But what I'm really doing is picking a rational realization and just hoping that it's kind of regular enough that it doesn't cause any problems. The other thing is you can kind of get around this problem by using variables instead of, so you would have p as a variable, map it over, do this, and you get a load of polynomials, but the sheer amount of variables you would have would be too large to actually compute anything at all. The Grosvenor basis just crashes. This slide has got a lot of information, but don't worry about it. What I'm doing here is I'm focusing on minimally d-rigid graphs. So this is, I take a graph that's d-rigid, but it has no proper d-rigid spanning subgraph. So if I remove any edge, it becomes flexible, effectively. And with these graphs, you have a lot more leeway on methods than what you can do. So you can use a random edge labeling and solve quadratic equations using Grosvenor basis. That simplifies things quite a lot. And it's quicker than the previous method I mentioned on the previous slide, but it's still kind of horrendously slow. So you can have a 10 vertex graph and it's taken over 2,000 seconds to even compute it. So it's not great, and it's still probabilistic. You can do the same method as method 1, but you can use edge lengths as variables. This is a definite algorithm, which is good, but it just completely crashes computers if you get to 10 vertices. So it's not really very useful. The last method is an algorithm developed by Jose Capco, Matteo Gallet, Georg Grasegger, Christoph Kushan, Neil Lubes, and Josef Schiko, who were mostly based in Linz at the time in Austria. And they developed an algorithm in 2018 from using tropical geometry. So very nice tropical geometry methods to break it down. And they got a combinatorial definite algorithm. And this algorithm is extremely fast. So it took 1.7 seconds in Mathematica to compute something that it would usually take 2,000 plus seconds with Grosvenor basis. And they can do much, much larger graphs. However, the algorithm is actually still doubly exponential. It's a kind of like a tut polynomial algorithm, except you're kind of doing tut polynomial with two graphs at the same time in a sense. So it's kind of slow, unfortunately. So after a certain point, it also still starts, your computer will start smoking when you try to do this. But there possibly isn't a way around this. I would guess that is probably always going to be kind of doubly exponential to work these things out, but I wouldn't want to say for definite, but that would be my guess. Right. Okay. What about when is the real realization number actually equal to the complex one? So they are actually equal for large classes of graphs. So globally rigid graphs, I already mentioned earlier, caudal graphs, it's always true in one dimension. There's a type of graph related to the two-dimensional rigidity matroid. It's whether your graph generates a connected two-dimensional rigidity matroid. This is a result of Bill Jackson, T-Bill Jordan, and some others. And that's another type. And in fact, pretty much any d-rigid graph you can think of, it usually seems to be true that this is, and it's usually quite easy to find in some sense. But is it actually true? Is it true that the real realization number is always equal to the complex realization number? And the answer is actually no. So it's not true. So we're going to take this graph above, which is a bit of a weird graph. And it was proven by Bill Jackson and John Owen only a few years ago that actually this one has strictly less real realizations than complex realizations. I've given a proof which involves Hendrickson's lemma, but all it basically says is that in this case, for this type of graph, it has to have an even number of real realizations. However, you can actually compute it using the previously described Austrian algorithm, and it has an odd number of complex realizations. And that's the proof. So you just check one number's even, one number's odd, that's it. They don't actually know what the real number is, but you don't need it to prove the statement. So it's a kind of a nice parity argument. these graphs are something I've been looking into recently. So graphs with odd realization numbers, and they seem to be quite rare. But this is work in progress, but it seems to be kind of provably rare that this sort of thing can occur. But that's a story for a later date. Okay. Right. Some quick asymptotic bounds. If we say that this function ftn is just the maximum number of maximum realization number for all d-rigid graphs with m vertices, then we can upper bound it by various asymptotics. So the first one is Borsian-Stranu. I'm saying Borsian-Stranu. It is kind of also the Bezout's bound, but they gave the Bezout's bound, but you could improve the constant in front in the O effectively, the linear constant. This was improved by Bartos, Emrys, and Shiko only a few years ago, but this improvement only worked for dimensions 5 and above. And actually, this was improved even more recently, so that you get this kind of horrible equation, which is asymptotically behaving like this thing on the right. This in particular shows that the number of 2D realizations is slightly less than 4 to the n, which is what you would get from Borsian-Stranu, and the 3-dimensional realizations is slightly less than 8 to the n, which is what you would also get. So there's been slight improvements on this. For the lower bounds on this, there's the naive one where you take the simplex and effectively just keep gluing simplexes together. That gets you 2 to the n as a lower bound, but you can improve on it. And there's been multiple improvements, and it seems to be kind of capping off at around, for the real ones, it's capping off at around 2.5 to the n. And for the 3-dimensional ones, it seems to have capped off roughly at 3.07 to the n. But this last number was done with probabilistic methods, so it could potentially be wrong. It'd be unlikely, but it could potentially be wrong. Okay. For the next thing I'm looking at, it's the minimum value of the realization number over all minimally d-rigid graphs with m vertices. If I just did rigid graphs, that would include globally rigid graphs, and then the answer would just be 1. So I don't want that. I want to do minimally rigid graphs. You can quickly prove that this number has to be bigger than, it has to be less than 2 to the n minus d minus 1. This is yet again done by gluing simplices together. And you can also prove that it's bigger than or equal to 2. And this is using this Hendrickson's lemma that I mentioned earlier. But that's it. We can't actually prove that this lower bound is bigger than 2, even though we do believe in the 2-dimensional case that it's bigger than 2 to the n minus 3. So the lower bound on this thing is just horrible. And we seem to be stuck in a bit of a rut on it. It's not the analog of this conjecture for 3 dimensions is not true. You can actually find graphs where it's got a lower number, but it still seems to be exponential, just not as exponential. And you can also prove that this conjecture is true for planar graphs in 2D. So if anyone has any ideas on this, this is a nice open problem in rigidity theory at the moment that no one really seems to know how to deal with at the moment. Okay. Right, so I've covered a lot about realization numbers of graphs. I'm now going to move on to the non-Euclidean variant. So, given a signature, so just a vector of 1s and minus 1s, I can now make another quadratic form. So I'm using d+1 coordinates this time, and occasionally I'm throwing in a -1 when I'm working out distances. So a standard one for hyperbolic space would be, maybe not hyperbolic space, but Minkowski space would be x squared plus y squared plus z squared minus t squared, where t is time. That's kind of a classic one. So with this, I'm going to define the complex pseudo-Euclidean space, h sigma. So all I do is I take all my points that are distance 1 away from, that have length 1, sorry, under my kind of weird quadratic form. And the distance I'll use for it will be this quadratic form I've defined above. Okay, so some examples. If sigma is just picked to be all ones, then I have the unit sphere. So it's just spherical space. It's the complexification of it, but yeah, it's the sphere. If I pick the first coordinate to be -1 and the rest to be 1, I've got the complexification of d-dimensional de Sitter space, which is something that occurs quite a lot in physics. Okay. With this, we can still define rigidity. I'm just going to skim through this, but we have a rigidity map. We just replace the domain with this hyperbolic or this kind of pseudo-Euclidean domain. And we replace the distance with this, our new quadratic form. Equivalence is now defined using the quadratic form, using this new rigidity map, sorry. Congruence is still defined via isometries. The isometries are slightly different, but you can still prove that it's an affine map, effectively. And it will have the same dimension as the previous orthogonal matrices plus translations. Rigidity, yet again, this definition is kind of wrong, but it's a rough idea of what it should be. Locally, you should have only finitely many realisations, and globally, rigid is now equivalent in this new setting. Everything that's equivalent is congruent in this new setting. So all the definitions are basically just the same, except I've just changed things to now be in this pseudo-Euclidean space. The reason why I'm skimming over this a lot is generic rigidity and generic global rigidity is just the same across the CD and all these various pseudo-Euclidean spaces. So the combinatorial rigidity doesn't matter. It's all the same. So if I talk about a graph being rigid, I can say it's rigid in any of these spaces. I have to be a little bit careful about global rigidity if I'm looking at the real versions of these spaces. There are some issues there, but I'm not going to go into that. But there's some technical issues with some of these pseudo-Euclidean spaces being a bit too horrible with this sort of thing. Okay. From this, we can still define our non-Euclidean, we can still define a realization number, but what we're actually going to observe is that we always have an isometry between any two of these spaces. So if I have one of these pseudo-Euclidean spaces and I have another one, I can always just have an isometry between them because everything's complex. So I'm just multiplying coordinates by I, the imaginary number, to change the signature, basically. Because this, not immediately, but it tells you that kind of the graph realization number invariant, the graph realization number is going to be invariant under our choice of signature. So what this really means is that there is one non-Euclidean realization number. We don't have to talk about for different signatures. There's only one. So this is kind of what you should think of as the d-dimensional spherical realization number, or the d-dimensional hyperbolic realization number, or the d-dimensional de Sitter space realization number, whatever you want to think of it. This is what this number is. It just tells you how things are happening when you're in a pseudo-Euclidean space with positive or negative curvature. Okay, and it's, like I said, defined basically the same. I'm not going to bother talking about the real realization numbers for these things. That is more complicated, but you can use this number to still bound it. So this is still a useful number to look at. That's a talk for a different day, but you can still define the real version of this. Okay. So computing this non-Euclidean realization number, you run into the same issues as with the normal realization number. So it's still slow, it's still difficult. However, we fortunately yet again have had the Austrians come to the rescue. There is a fast algorithm in 2 dimensions when we're looking at minimally 2 rigid graphs. And we can use that to kind of understand a lot of things. And the first thing you understand is that the realization number and the non-Euclidean realization number are not always the same. So this is yet again the 3 prism. You'll remember from earlier, it has 12 realizations. Well, actually, it's got 16 non-Euclidean realizations. And here's an example where it's the 16 realizations of the 3 prism on the sphere, which is compared to the 12 realizations previously when we were in flat space. So you can actually get more realizations when you're on the sphere, which seemed quite quirky, but no one really knew anything about it. Actually, I'll skip this slide. So that property that I said before, that seemed quite quirky, and no one really understood what was going on. Someone being Georg Grasegger in the RICAM Institute in Linz, he sat down and just computed a ton of these numbers. So he took all the minimally 2 rigid graphs with 12 vertices and minimum degree 3. The only reason he did minimum degree 3 is if you have minimum degree 2, you can kind of remove the degree 2 vertex and still have a rigid graph. So you're effectively just increasing your set of numbers without really gaining very much. So he doesn't want to do that. He computed all these numbers, plotted them on a graph, and then noticed that they all sit above the y equals x line. What you can kind of see in the picture is not really so easy to see. If they tend to be close to the line, they tend to be small. If they tend to be far away from the line, they tend to be quite big. And you can kind of see in the dark patch that actually most of them are kind of concentrated not on the line. And you can prove that actually the number, well, not prove, but it's been observed that the number of realizations where the 2 numbers are the same is actually, it seems to be very small. So most of the time you will have more realizations on the sphere than you will in flat space. Okay, which seems kind of counterintuitive because rigidity and global rigidity and all that is the same. But now I'm telling you, actually, if you're not globally rigid, you're going to have more realizations if you're on the sphere. Okay. Mine and Georg's proof on this was that we proved that this is actually true. So this observation is not just a computational observation. We actually sat down and proved that it is indeed true, that you're always going to have at least as many non-Euclidean realizations as you are realizations. Okay. So how did we go about proving this? What we used was an idea called coning. So coning is a way in rigidity theory to take a graph that's rigid in 1 dimension and go to 1 dimension higher to obtain a rigid graph in 1 dimension higher. So what you do is you take your rigid graph, say the graph I have here in 2D, I add a new vertex in 3D and I connect it to all the vertices in 2D, and I now have a rigid graph in 3D, basically. And in fact, I kind of have a rigid framework in 3D. That's kind of, it's not immediately obvious, but effectively you replace your edge conditions with triangle conditions, and that's why this works. Walter Whiteley, who's based in Toronto, I believe, he proved that a graph is actually rigid, is d-rigid if and only if its cone is d+1 rigid. So this coning works both ways. Now, what me and Georg realized was actually that with the realization number, if you have a graph and you cone it, then the realization number is d+1 dimensional realization number is actually equal to its pseudo Euclidean realization number, the dimension below. The sort of idea why this works is where I have the picture of that framework and it's flat in 2D space and I've added the vertex and connected it, you can actually prove now that if you slide the vertices along these bars up and down, the realization number doesn't change. So what you can now do is just slide them until they're actually all distance 1 away from the central one, and you have a spherical realization. That's kind of the trick. So that's the trick that works there. Okay. So with this in mind, we're ready to prove mine and Georg's thing. So this is a completely wrong proof, but it is correct in the sense that it gives you the right idea of what we did. So by the previous result, we know that it's actually sufficient for us to show, oh, it's not an equality. Oh, apologies. So it's enough for us to show that CDG is less than or equal to CD plus 1, the cone of G. So what we do is we think, okay, how does the d-dimensional realization look if we think of it in 3D? Well, one way to kind of think of it is we have a point at infinity, and it's connected to all the points. So we take the cone of the graph. So take this picture, we take the cone, we put the vertices flat in the plane, and we put that top vertex just at infinity. And when we do that, it forces all the bars to be collinear, and it forces all the vertices to just stay in the plane. None of this makes any sense in what I'm saying, but this is kind of the correct idea for what's going on. What you then prove is that, okay, when I do this, I'll get a realization. I'll have a realization number. And when I perturb to something generic, the realization number can only jump up. It can't decrease. And this is like an algebraic geometry sort of thing. Yet again, this is kind of not true in general, but we can prove in a kind of an algebraic setting, in our setting, that this is true. Because perturbing can only increase the realization number, we then have to have more non-Euclidean realization numbers. And that's the proof, QED. Yet again, this is not the proof. There's so many technicalities in what I've just said. We have to kind of rebuild the whole system from scratch to describe the geometry constraints. But yes, this is kind of roughly the thought process that went behind it. Okay. With that in mind, how much of a difference can the two numbers be? So we saw in the previous picture here that the numbers can differ. And if you look at the picture, you can kind of see it kind of gently slopes away. There's quite a lot above the line. And some of them are very high. So there's one very much at like right at the top. It's got over 6,000 non-Euclidean realizations, but almost less than 2,500 Euclidean realizations. So the question is, how much can this differ? So we define this theta. So theta dn, it's just the maximum of over, you take all your graphs that are minimally d-rigid, you take the pseudo-Euclidean number and you divide it by the Euclidean number of realizations. What is this number? And the first thing you can prove is that this is bounded by an exponential. That's not too bad to prove. So it's going to be less than or equal to some linear constant times alpha to the n. This alpha, you can also prove quite quickly, has to be at least 1. But it's hard to prove that it's actually bigger than 1. So we conjecture that it's true for all dimensions, that this value is actually bigger than 1. We can prove it's true for 2 dimensions, and we can have some nice bounds on it. So, and we can kind of improve these bounds if various conjectures about realization numbers is actually true. So the upper bound, how we get the upper bound is we take the upper bound on the number of pseudo-Euclidean realizations, which has been done previously, and divide it by 2, effectively. And that kind of gives us that top number. And the lower bound is done by finding a realization, a family of realizations with lots of pseudo-Euclidean realizations, but not so many Euclidean realizations. And the one we do for 2D is to take this graph down here. It's got 864 realizations in the plane, but actually 2,048 on the sphere. And we just keep gluing them at triangles. And this gets us very, very large graph with lots and lots of pseudo-Euclidean realizations, but not so many kind of flat planar realizations. Okay, so that's the main part of the talk. I'm going to briefly talk about a small breakthrough that happened last week. So I mentioned previously that if a graph spans another one, then we can talk about this equation here. So if G has a spanning subgraph H, then we know that G has less realizations than H. and it has, yes, less pseudo-Euclidean realizations than H. But what we can actually prove now is that if you have a rigid graph with a spanning G with a spanning rigid subgraph H, then actually you can divide the realizations of H by the realizations of G. So it's some multiple of it. And the proof's not actually that complicated. You just kind of follow your nose with a lot of the geometry of these things, and you kind of get it through that. And this was from a recent project with quite a few of us working on tropical understanding realization numbers using tropical geometry from a nice project grant from the Harbour Institute in Bristol. Okay, so what's the application of this? The first application is a bit bizarre. So if we take the graph on the left, that graph on the left is globally rigid. And the way in the plane, sorry, the way you would usually prove this is using Connolly's theorem and Berg and Jordan's theorem. You could also use Jackson and Jordan's theorem for the second part. So you have to use quite a lot of heavy machinery to prove it. Our proposition basically says that, okay, well, we know that the graph contains two minimally rigid subgraphs. So that's the graph on the middle, in the middle, the graph on the right. Their realization numbers are 45 and 32, respectively. We know that the realization numbers, the realization number of our graph on the left has to divide both 45 and 32, but they have no common factors apart from one. So therefore, the graph on the left has to have one realization, therefore it's globally rigid. So that's a nice result right there. It's a very specialist result, and I'm not saying it's going to go further for proving anything about global rigidity, but it's a nice way of proving it. We're not having to use any sort of very heavy algebraic geometry. We're just using this kind of nice, easy combinatorial observation. The next is about global rigidity augmentation. So often if you have a graph that's rigid, you actually want to add edges to make it globally rigid, and it's kind of a hard problem. It's provably a difficult problem to get estimates on how many edges you need to throw in to make something that was rigid actually globally rigid. And we can kind of use this division thing to tell us. So if we have our realization and it has a prime decomposition P1 to PK, so in the last one we had 45, for instance, that would have a decomposition of 3, 3, and 5. Then the length of this decomposition tells you how many edges you need to throw in. Because every time you have the possibility, every time you have a realization where the number is not equal to 1, then there has to be a non-edge you can throw in to reduce the number. And every time you reduce the number, it has to be a factor of what it was previously. So if you have k primes, then it has to be size k, has to have, the new one has the realization with at most k minus 1 primes. And you just use that to prove it. So it's kind of just a silly, quick argument. The last one is that if you do this operation, which looks quite complicated in how I've written it, but the 2D version is you take a triangle, you split the edge. So you delete an edge and you add a new vertex adjacent to the 3 previous edges. This is called a one extension. This is the 2-dimensional one extension, but you can do the d-dimensional one extension. You don't necessarily need it to be a simplex, but you need at least one edge to do it. This is the special case when you are doing it to a simplex, in this pictorial case, a triangle. It was previously shown by Jackson and Owen that this will actually just double the number of realizations, but we can actually show that it exactly doubles the number of realizations. And we have quite a clever argument using this factorization method that we previously just described. Okay. Thank you for listening. Sorry about the mistakes in the slides, but yes, that's the end of my talk. So thank you for listening.